My name is Brian House. I'm the Chief Commercial Officer here at Neural Magic, and today's session is called No Hardware AI, where I'm going to tell you a little bit about the next era of machine learning, according to myself and my colleagues at Neural Magic. So before we get started, let's do a little bit of housekeeping. So we will be recording today's session, and this recording will be posted and shared via email within 48 hours. So if any of your colleagues missed it, you want to share it or forward it to a peer or friend, you're welcome to do that. Additionally, we'll be taking questions in two ways. So you can ask us questions on Twitter. So use the hashtag #NoHardwareAI to ask questions or make comments. And given that it's Cinco de Mayo, the top tweeter will get using our hashtag, will get a margarita kit. In addition, you can ask questions via the Q&A tab here in Zoom. So feel free to do that as well. And that's a good piece. So what we want to do, actually, that's funny. So we have a Q&A tab. So use the Q&A tab, and and you can type your questions in at any point during the session. This is a little confusing on the slide, I just realized. But why don't everybody give it a try and use the Q&A tab to submit a question and specifically tell us where you're dialing in from. Let's see where folks are. All right, we have Washington, D.C., Ron in Pasadena, a few people from the D.C. area. Excellent. This is great. Oh, London. Thank you, Manny, for joining from London. So apologies on the confusion here. Oh, we have someone as far away as Lithuania. Rightus, you might win as farthest away. Another person from Wrocław, Poland, Copenhagen. Awesome. So we have a gathering from folks around the world. Impressive. Peppo from Italy, a few people from Western Canada. Steve, you're dialing in from Honolulu. I would think the surf would be breaking about now, but awesome. Well, thanks everyone for joining from all over the world. Super exciting. I see people in chat too. So that is very cool. We'll fix this slide. So there's only one place to submit questions from. And I also wanted to say happy Cinco de Mayo. So we're very excited here at Neural Magic that Cinco de Mayo, May 5th, happened also on Taco Tuesday. So we'll be celebrating the rest of the day after the webinar. So appreciate that. Hopefully enjoy your day. And with that, would love to get started. So appreciate everyone joining. As I said, we're going to talk a little bit about the next era of machine learning and no hardware AI. So what's the story of Neural Magic? So really, the background for us is our company was founded out of MIT by two MIT folks, a professor, Nir Shavit, and his longtime student, Alex Matviv. So this was these two gentlemen have spent their career studying multi-core programming and high-performance computing. Nir wrote the textbook on multi-core programming, and they had diversified some of their work and were doing research in computational neurobiology as a way to diversify what they were working on, and came across an interesting deep learning problem. They were doing research to map the connectome, all the neural pathways and synapses within the brain, and needed to take a cubic millimeter of brain tissue, slice it 30,000 times, run it through a microscope, and run deep learning images on it. And turns out that is a massive amount of information. It comes off at a terabyte an hour. And that means they needed a lot of GPUs to run their segmentation models, to run and find all these pathways. And they didn't have any GPUs. So they rethought the problem and thought about how to compute these deep learning models and apply some of the principles they have. And out of that came some of the insights that led to the foundation of Neural Magic. So In some ways, this is a little bit of a found secret. I joined the company soon thereafter, and we also have Brian Stevens as our executive chairman, who is most recently CTO of Google Cloud. So we have a strong team, a lot of PhDs, very much focused on high performance computing and deep learning. So hopefully you'll see that in our product. Fundamentally, the problem, as we see the world, is we really believe hardware is constraining deep learning's potential. We've seen, the practice of deep learning and machine learning really grow with the adoption of specialized hardware accelerators like GPUs and come into the market. But in doing so, they've introduced a bunch of constraints that are hampering deep learning as we see it. These machines are costly. They're costly to buy. They're costly to run in the cloud. They're costly to operate from a power, networking, weight, any way you look at it. They add all sorts of complexity to the machine learning pipelines. Because your software and your CI/CD pipelines now need to be hardware aware, suddenly you're rewriting things from containers, virtual machines, deployment software, everything to take advantage of these resources. And then most importantly, they're limited. They're memory limited, which constrains the input sizes, the types of models that you can ask, the size of models, and the number of models in a pipeline per device. But we accept all of these constraints because the alternative, running these on CPUs, is just too slow, or has been historically. And that's really, was at the premise of what we went out when we started the company to go solve. And so as part of that, what we developed is a software runtime engine, and that's at the heart of this idea of no hardware AI. And so utilizing Neural Magic softwares today for inference and tomorrow for training, what we are able to do is address these three critical problems as we see them. And we deliver GPU class performance without GPUs. We give you a modern containerized scale out environment, software that fits right into your CI/CD pipelines, makes it easy to deploy and manage that software as you manage for any application. And because CPUs come with an order of magnitude almost more memory right out of the box, and it's cheap to add additional memory, you can do have larger input sizes, you can do high-res video, you can have multiple models in a pipeline all in shared memory, all of that leading to better predictions. And so at the highest level, these are the problems that we've set out to solve. I'm going to talk about each one of these solutions today in our webinar. So how does it work? So as part of Nir and Alex's research, they've sort of came across two critical performance insights that led to ultimately the performance, the ability to achieve that performance on CPUs, and sort of how we rethink this problem. So the first is this idea of recalibration. It's applying unknown and understood techniques of sparsification and in the near future, quantization to deliver performance. And so we're going to talk a little bit how you can prune models and reduce their computational requirements and achieve performance out of that while giving data scientists fine-grained control of both their accuracy and performance in terms of speed, image process, as well as performance in terms of accuracy. And typically people use techniques like sparsification as a way to shrink their models, to fit them inside the memory limitations. And certainly that works, but in doing so, they haven't been able to achieve performance. In some ways, have significant degradation of accuracy as a part of this. So that's the first piece, is about applying known techniques in new ways to achieve performance from that. The second insight we had was that most of these models are memory bound. So yes, there's certainly a lot of computation that goes on in a deep learning model, but they're also memory bound. And what we've seen when you look at successive generations of hardware accelerators, as they add additional flops to the machine, performance does not scale linearly with the number of flops. And what that means is that the computational horsepower only has so much benefit. Eventually, you hit memory bottlenecks. And so this is where our team's multi-core programming background comes in to help. What we've defined as a set of algorithms that accelerate the memory-bound processes inside the deep learning models. And so we're able to take advantage of the cache hierarchy in CPUs and minimize, if not eliminate, data movement in order to generate additional performance. And so what we can do here in summary is we reduce the amount of computation required and we get performance from that, while we're also accelerating memory-bound processes and getting performance of that. And that combination of that too is really how you'll see the numbers that we deliver here, how we're able to get deep GPU class performance right on CPUs. And if many of you, if you've seen the talk to us, this is the part of the presentation I'm sure you've seen before. We'll go in further into some of the details here. So where can you use Neural Magic today? So we're focused on computer vision. So you can use our software for two primary use cases. The first is image classification, and the second is object detection. You know, we're a small startup, we're 25 people, so we try to remain tightly focused on the use cases we're attacking from a go-to-market perspective as a way to ensure that we do a few things really, really well, and then we'll expand over time. We're looking at things like segmentation models, NLP, and transformers are all things on our roadmap that we're talking about now. But today, we're focused on classification and detection. And our value proposition is twofold. One, it's reduce your costs. You know, as we talk to data scientists and machine learning engineers, they have lots of models out in the wild, running in clouds. We have organizations that are building large data centers. And so we help them dramatically reduce the costs of their machine learning deployments, reduce the IRR necessary to put a new model in a new application into deployment, and give them the flexibility that software has to deploy anywhere. Oftentimes, you know, one of the things we're hearing a lot lately is more and more data centers coming on in metropolitan environments and edge environments that don't have GPUs, but that's a great place to deploy machine learning models and applications. We can turn those into deep learning centers as well. And the second use case is around GPU replacement in environments where it doesn't make sense to add a hardware accelerator, whether it's a homogeneous data center environment, it's an edge deployment, it's in a physical location, places where it just doesn't make sense to have an attached GPU, we can take advantage of the compute infrastructure that's already there. We'll talk a little bit about the models that we make available in our model repo that's part of the product. So let's give just a high level view of our product offering and what's available today, and then we're going to dig into the areas that have numbers to provide more detail. So first off, we provide a set of tools for the data scientist who's responsible for building models and making those models performant, both from an accuracy and a processing perspective. So obviously within this, we work within TensorFlow and PyTorch, as well as Keras, which is on our roadmap. And we provide a Neural Magic model repo that sits alongside your own client model repo, the model zoos that come with these machine learning frameworks. And in that model repo, we provide a set of pre-trained, performance-tuned models. And so you can choose as a data scientist to work with one of our models that's pre-tuned out of the box and use our transfer learning tools to learn that on your data, or you can take and use your own model and then use our recalibration tooling specifically for sparsification and pruning to apply these known techniques to reduce the amount of computation in your model and ensure that it drives better performance when run on a CPU environment. And so all of this lives within this. You can also run models in dense mode. You don't have to sparsify models, but you can. We provide you the tooling that does that. And then the output of this is a representation in the form of an ONNX file, which is an open source standard, the Open Neural Network Exchange, that we take and then move into our inference engine. So on the data science side, we provide a repo and tooling to help you get performance and tune those models. We'll talk a little bit about that in further detail. And then secondly, we take that model representation in the form of an ONNX file and we input that into our inference engine. So for the machine learning engineers, what you do is you install the inference engine in the form of a binary inside your model serving solution. And this could be, you can call it via Python API. You can set this up as a RESTful service. You can install it within your own serving solution that you're already using today. We actually also ship with the Onyx runtime server out of the box. If you don't have a model serving solution, you can use that as well. And all of this works if you deploy via Dockers, you can deploy it via virtual machines. You can take advantage and deploy it on bare metal and can run on-prem, in the cloud, or on an edge device, so long as it's an x86, Intel x86 chip. The software installs in user space and can run there. So you can think of this as running in the same way that Intel MKL or CUDNN are deployed and run. Our inference engine, our library, runs the same way. So with this, what I'd like to do is actually do our quick first poll of the day. So we've got 3 polls today, and so this is a quick poll. So if you just take 1 second to respond, the question is which deep learning framework do you utilize? We hear a lot in our customer conversations about different frameworks we use, and so this is super helpful to help us understand what folks use. We would imagine that in many cases we hear that people use more than one, but not surprisingly, the majority of folks are using TensorFlow, almost 83%. So that clearly jives with what we're hearing in the market too, in terms of the popularity of the different frameworks. Awesome. Thank you for that. I'm going to give it 1 second more. All right. Awesome. So, and that, great. Moving on. So now let's dig into the 3 components that I talked about and talk about each in more detail. So let's go in there. And I see some questions starting to come in, so I will answer those on the way. So the first question, before we go too far, is from Ron. It says, is performance gain only in inference, or is also a performance gain in training? So thanks for the question, Ron. So today, our software only works for inference. We do not offer a training solution. As part of the work we were doing in connectomics at MIT and Harvard, we actually built a prototype for training on CPUs, and we saw similar performance, what you see here, in prototype form. And so on our roadmap is actually to build the same on CPUs at Neural Magic. We just haven't started that project yet. So one thing at a time, you know how these things go. All right, so let's dig into here. So I mentioned before the model repo. So this is an option that's available to you, and this is a repository of models for both image classification and object detection. And so what we've done is we've provided a set of models that are pre-trained and pre-optimized according to a couple different criteria that are available for any data scientist to use that utilizes the Neural Magic software. So on the classification side, you see things like ResNet, MobileNet V1, V2. We actually have efficient nets, both B0 and B4, as well as VGG. And what we do is we provide multiple versions of each one of these models. And this is a way for you to start to see sparsification and pruning in action. So the first version is the dense model. So it operates as you'd expect it to, just like the open source version, right? No different, no change in that. The second option we provide is what we call sort of the recal or the recal accuracy version of the model. And so this is a model that's been pruned in many cases substantially. So in the case of ResNet 50, 90% sparsified, but it retains 100% of the baseline accuracy. So it has the exact same accuracy as the dense version of the model. It just has a lot less computation. And then the other thing we do is we provide a recal perf version, or performant version, where we give up 1% of accuracy in order to gain a little bit better performance. And so we provide multiple versions of each of these models, and we encourage you to test and try those in there. And these models are available for both PyTorch and TensorFlow. And we have Keras support coming on our roadmap as well. And on the object detection side, as you can see, we're focused on SSDs to start. So those are interesting, and we provide MobileNet and ResNet versions of backbones for SSDs, and those are provided in TensorFlow today as well, and we have Keras on our roadmap as well. And so one of the questions we got, another one from Ron, is do you have to use a model from the model repo, or can you use your own custom models? And so absolutely, you can run your own models on the Neural Magic toolset. And I'll talk a little bit about that in a second when we get into pruning and how you can do that. But oh, that's going the wrong way. But first, we have our second polling question. So the question I have for this group is, which deep learning models do you guys typically use? So we've provided a selection of these. So curious to see which of any of these models that folks are utilizing for their deep learning needs. All right, so I'll give you guys a minute to come out and provide responses for these. Interesting, not surprising. ResNet is the leader in the around turn one, if you will. Excellent. Lots of folks utilizing MobileNet, and more folks than I would have guessed using EfficientNet, which is great to see. Excellent. So while you guys are filling this out, there's a question in here: is which CPU chips do you support? x86, ARM, others? So the answer to that is today we support x86 chips, and I'll talk about this a little bit later when we get to the inference engine. And what we're doing is we're taking advantage of the AVX instruction set specific to Intel x86 chips. So you can run on any Intel chip from 2014 and beyond since the Haswell generation, and you can run on those on AWS, Azure, GCP, any of the public clouds. We can even give you instance recommendations for instance types if you want to run on those. Those are all available, yes. All right, so thank you for voting, giving us. So 73% of folks use ResNet 50. The next big winner is ResNet 50 SSD, which is great to see. And then there's a bunch of people using MobileNet and 4 people using EfficientNet, which is great. All right, thank you. So let's jump into recalibration and how you can apply the pruning tools and sparsification tools we have to your own models, rather than using one of the pre-optimized ones. And so, I mentioned before that one of our key insights coming out of the work we were doing Nir and Alex were doing in Connectomics was this idea that performance can be achieved through sparsification. And so what the realization we had, and more research is coming out on this, is that most of the weights in a neural network are useless. And they can be removed with little to no effect on the loss associated with them. And so just some examples that have come from research here: you can sparsify ResNet 50 by 90%, set MobileNet by 75%, even a transformer can be sparsified up to 60% without any meaningful loss in accuracy to those models. And so we, based on the work we had done in the past, we recognized this and said, how do we get performance from this? And so the sparsity is useful for a couple different ways. So the one I mentioned earlier was this idea that you can reduce the size of a model to make it available for more deployment options. So in the bottom, you see VGG is typically a 500 megabyte model, but with pruning, you can reduce that by 49x. Now suddenly you can make that available for deployment and edge deployments on smaller devices. And that's typically but what we've seen the utilization of sparsification until recently for. And then sort of one of the insights and one of the things that we've been able to develop at Neural Magic is the ability to get performance from that sparsification, not just shrink it, but actually turn it and make it faster. And so if you look at ResNet 50 on a 4-core CPU, a few years ago, it would take hundreds of milliseconds to run a single image. And today that's improved a great deal down to tens of milliseconds. But when you utilize Neural Magic's inference engine, we can do that in less than 10 milliseconds, a 2x improvement in speed. And so, what we've been able to figure out and develop here is algorithms that accelerate that sparse computation and really make that even faster. But one of the things, we did a survey, and you can see the link for it, and the survey is still live if you haven't taken it, so I encourage you to do so. When we talk to customers and we talk to people via survey, we see few people are taking advantage of some of these optimization techniques, things like unstructured sparsification and structured pruning, to improve the performance or size of their models. And so this came out of a survey we did. We had 290 responses. You can see a link to the survey results in here, but we were actually really surprised by this as we think about the performance potential for things like quantization and sparsification. We were surprised to see very few people were actually taking advantage of these techniques. So this comes to our last quick poll, which is, are folks using optimization? So let's just quickly do this here. Or have you done any optimizations on your models specifically to improve performance for production? So we'll see here if people's experience has been similar to what we saw in our survey environment. All right, and so actually it does see about the same. I think that quantization is definitely moved up a little bit, about 25%, but no optimizations is still at 57%. So very, very consistent with what we saw with our survey. And so thank you for responding to our polls and giving us that insight. And so this was a big question that we asked ourselves, is why are people not taking advantage of these techniques that, at least from a research perspective, are pretty well understood? And the reasoning we found was sort of insightful. So first off, this pruning or sparsification takes a lot of inputs to make this successful. It takes resources in terms of people and time, it takes practice and intuition, it takes tools in order to do it and do so effectively. So when we evaluated our survey results, one of the things we saw was we looked at the implementation of optimization like pruning and what have you, and the size of the data science team. It turns out it makes a huge difference. You have a small data science team with less than 10 people, very few of them, less than 10% of them have pruned models. As soon as that team grew in size, we saw almost a 3x increase in the number of people doing pruning, implementing those capabilities. But even then, we're still talking less than 20% of the overall market. And so, as we thought about this, I think there's an opportunity here, and this is why we're building our recal product. So first is pruning takes a lot of learned intuition. There's a lot of experience involved. It's a lot of time and energy and practice to see that. And frankly, as we look into the survey of the market, there's a lack of support and ease of use across the machine learning frameworks. A lot of this market today is still DIY. And so there's a lot of tools that are available or aren't available there. And so you're sort of on your own to figure out how to do it. And then in the deployment side, the systems that you use to deploy these options don't support unstructured pruning. And so what we see is the techniques are struggling, team size is dependent on this, and the tools aren't there. And we looked at this and said, really, the opportunity isn't in structured sparsity, isn't in sort of making significant changes to the model and removing weights altogether. in order to get performance, but actually the opportunity is really an unstructured sparsity, where all we're doing is turning off activations, not making changes to the model. We're just changing the algorithm and the path in which we're executing that model, such that we're being more efficient and we're not taking on unnecessary computation as a result. And so this is one of the ways in which we're able to get performance. And then what you see here is our Neural Magic tools that are available. So this is the first iteration of our recalibration tool. We deliver this in a Jupyter Notebook interface, and we're building a UI for this that has a lot more sizzle than what you see on the screen here. But the goal of this is to simplify this process to enable more and more people to take advantage of it, and then to provide the infrastructure in the form of the Neural Magic Inference Engine to allow you to get performance from that, from this exercise. So what we've done here is we build intuition all into an easy to use UI. So you can do this in the UI right in the Jupyter Notebook, or you can do it from the command line with just a few lines of code. And what we do is we give data scientists hands-on controls so they can see, you can see here, we can see each one of the layers in the network. We can set our desired sparsity by layer. We can determine how many epochs, which epochs the pruning starts and stops. How do we want to recover our accuracy in there? And so we give you lots of controls to figure out, how to trade off accuracy and performance, but at the same time, we constrain some of your choices based on the deployment environment. So we're sort of set a narrow bound in which a data scientist can operate in order to get performance and simplify a lot of the actions and take some of the guesswork out of it. And as we look at this, we think there's a huge opportunity for this, and so we're increasingly building more and more automation into this to make it easier for data scientists to get the best performance out of the models they have as fast as possible. And at the end of the day, we save all of this to a YAML file, makes it easy to push to deployment, makes it very simple to fit right into your CI/CD pipelines. So we're very excited about this. We're looking forward to, as part of our beta program, into people getting hands-on experience with this and try this on their own models. So one question here from Manny on this is, how much work is it to convert legacy models into Neural Magic models, and is it possible to backport them to legacy ones? So the amount of work necessary to sparsify or prune a model is, frankly, is equivalent to the amount of work you would go through to quantize a model or calibrate a model for quantization. So as we've experimented, run, and talked to folks, that's about the equivalent. So you take a trained model, you run it through this process, and then and you get sort of a optimized version out the other side. So it's not there's machine time involved, certainly, but it's not a ton of data science time, and our goal is to accelerate that. And so we'll to give you a sense of how much time it is. All right, let's move on. So now we've talked about the model repo. So we have pre-tuned things out of the gate. We talked about sparsification tooling and recalibration. So the tools we give to prune your own models. And then we can give you, let's talk about the inference engine and how we run that. All right. So the inference engine. So this, as I said, is a runtime environment that sets, it's deployed in your model serving environment of choice. If they're TensorFlow serving, Onyx runtime, as we said, we shipped before on ours. As I mentioned, we run all on Intel x86 CPUs. And so the key is the AVX instruction set. So we can run on both AVX2 and AVX512. And obviously we run better on AVX512. And so the way the inference engine works is that, and you'll see this in the demo, I'll show you this, but what we do is we compile an executable upon startup based on 4 inputs. So what's the model file? What's the CPU instruction set that's on the CPU? What's the batch size that you're running in the application? And then how many cores are you going to run it on? So you could, if you have a 18 core CPU, you can choose to run it on all 18 cores, or you could run it on 4 or 8 or any combination of those underneath. And so those 4 inputs all happen or inputted into the compilation phase, and outputs generates an executable that you can then run and drive your inference application through. And then as a data scientist, you can, or as a machine learning engineer in your application design, you can invoke the inference engine either via Python API, or you can actually deploy it as a service and service enablement right in a Docker, and then invoke it via REST API. And so it's very easy to fit into your existing deployment architectures, whatever they may be. And we're very interested in talking to folks about that. And then as we've been talking to customers, most everyone is telling us they deploy their machine learning applications via containers, and they manage those in Kubernetes. And so this will fit very nicely into that as well. You can deploy containers, manage them, and scale them up and down with Kubernetes as you see fit. So I'll show you a little bit more of what that looks like in the demo here in a few minutes. But first, let's go through and look at some performance numbers to give you a sense of how all this works, how all this performs in practice. So this is ResNet. And so what you'll see here, and this is consistent across all the performance slides, is you'll see a combination of CPU different options. So we run it on a 4-core CPU, as well as on a 18-core CPU. These are C5 instances up on AWS. And then we compare those, the raw performance here, against the T4 inference chip, as well as a V100, the Volta from NVIDIA. And so this is ResNet. It's a great architecture design. It's the most popular image classification one based on our poll today. And we're running at batch size 1 here in this performance test. You see, we've been able to deliver up to 2x better performance just on a raw performance basis. And this is a network that's designed and made for, the ResNet for the GPU architecture, and very much for the sort of dense computation that a GPU does really well at. But then if we look at it from a price performance perspective, where we're actually calculating the number of images in the millions per dollar, what you'll see is the benefit of the CPU and deploying on a CPU. So we have much better price performance because the cost of a small CPU, a 4-core CPU in this case, is so much less. It's 10x less than the price of a V100. And so you see much, much better economics associated with that same application, batch size 1 at FP32. And all the comparisons to date are at FP32 across the board, because that's the only precision that we support with. We're currently building quantization, and so we'll soon offer FP16 and int 8 support, but we don't offer that to date. So that's ResNet. But now if we look at different models, like this MobileNet V2, what you'll see, this is a much less dense computationally model. It's more sparse by design, and therefore it's more memory bound. It's not quite as computationally intensive as a model like ResNet. And you see both the 4-core CPU and the 18-core CPU at batch size 1 are doing exceptionally well in raw performance. It's a 7x compared to the T4 and the V100. And then, not surprisingly, just crazy from a price performance perspective, that multiplies through when we look at it from economics. We even look at larger batch size. The things we would expect to happen are, so this is MobileNet V2 again, but this is at batch size 64, right? So what you see here first and foremost is that we've saturated the cores to the V100. So the performance of the V100 goes up as one would expect for very significantly. But the 18 cores is keeping pace, which is great. And it's 3x better than up to 3x better than the T4. But then if we look at it from a price performance, the pattern we've seen holds true, because the price difference between the 4-core and the 18-core is so substantive. We still see that 3x better price performance even at batch size 64. So you pay a hefty premium to get that performance with the larger batch size that the CPUs can compete with in the 18 core, and obviously from a price performance perspective, do exceptionally well. And then the last one I want to show here is efficient nets. We saw a few people doing this. Thing that we really like, or we find very intriguing and full of possibility from an efficient net perspective, is this. We really think this is the future of neural network and deep learning model design. And so efficient nets have 20% of the compute of ResNet with the same level of accuracy, right? So it's based on this premise that it's easy, we're getting better and better at finding the sparse algorithm hidden in all of this dense computation and getting an answer without requiring as much computation. And so this is a scenario where flops aren't going to solve the problem. We actually get great performance from the CPU. There's a lot of memory bounded components of this, and so you see our performance looks exceptionally well. So not only are we great from a raw performance perspective, up to 6x better, but then really, really great price performance. And so from a deployment characteristic, from an IRR perspective, for an organization considering how to get more deep learning applications into production, we think these are critical pieces. We have the flexibility of software to deploy them in many, many more places with much more abundant resources at much more price performantly at scale than compared to some of the other options that are available to data science and machine learning engineering teams. So a couple of questions here. So one with, how does the T4 outperform the V100? That was because batch size 1 in that example. We talked about different batch sizes. And so one question, Sace asks, do you require model retraining to get these performance improvements? So in the ResNet example, we did. That's a sparse version of ResNet, the sparse accuracy model. And so that required the recalibration or retraining to deliver performance. In both the mobile net and in the efficient net examples here, we ran those in dense mode. So there's no sparsification, and therefore no retraining is required at all. That's one of the things that's really interesting about new model architectures is as they become more and more sparse and require less computation, there's a lot less, in theory, sparsification necessary to get performance, although we're delivering recal versions of each of those models to allow you to get whatever available performance gains there are, and there are definitely some. Cool. So with that, we are ready for the demo, and I think we're doing pretty well on time here. So keep your questions coming in the Q&A. I'm following that. While I do the demo, I'll look on, I'll see if I can see what's in the chat, but let me pull up the demo. Awesome. So let's just see. Somebody tell me if you can see the my Jupyter notebook here. Just give it throw it in the chat or in the Q&A and let me know. Let's see. Yep, visible. Great. Excellent. Thank you. So what we see here is an image classification demo. We're going to run through two things. So the first thing, what we're going to do is we're going to set up. We're going to configure a model. I'll let the audience select the model. We'll select the number of, show you how we select images and see how it runs. And so you can see this just from start to finish, how this operates, and I'll talk a little bit about that. And then at the end, what we'll do is we'll benchmark that model in a couple different core and batch size configurations, and we'll do this right on the fly. So we'll just run here. So what you see here, first thing we're going to do is set up the compiled model. So first thing we want to do here is to determine how many cores we're running on this machine. So this environment is actually running on a 4-core C5 2XL instance on AWS. So it's a 4 physical core machine. So it runs and detects that easily enough. Now we're going to select our model. So I'm going to run this, and what you'll see is this is pulling right from the Neural Magic model repo as it exists. So we see we have MobileNet, base, recal performance. We just have the base model of MobileNet v2. ResNet base, recal, repel, perf, and then the VGG. So there's a few more that are coming before release. So I'm gonna let someone pick a model. So I'm gonna go back over here. Somebody somebody pick a model that you would like me to run in chat or in Q&A, either way. All right, MobileNet. First one wins. So let's do MobileNet recal. Just to show, this is a sparsified version. 100% baseline accuracy is MobileNet. So then what we'll do is we'll create the model. And so what you'll see is, as I mentioned before, what we do is we take the file path, the batch size, the number of cores, and we compile that model. So I'm gonna run. And then it comes based on those inputs, it compiles that model. And so this is what happens at startup. Obviously, that was very, very fast. So when you're scaling out and adding machines, this happens exceptionally quickly and you can run. So batch size, number of cores, AVX 512. Great. Now let's pick some images. So we've got a whole list of images from the ImageNet data set. I'm just going to randomly pick some images. So we got these. So we've got spiders and snakes and crocodiles. So we got a bunch of those. Great. Now we can execute the inference model. So what we'll do is we'll run the model. And in that, what it'll do is grab the input images, the 6 we picked. It'll run those for execution, put them through the end time. It'll outputs a probability distribution. And then what we display is the top 5 predictions. So this is just the MobileNet recal running on the ImageNet dataset, and so it's delivering what we'd expect with the relative accuracy that you typically expect from ImageNet and from these. So it struggled with the barn spider. The rest of them it actually did pretty well. So all of that runs. So we've demonstrated that it actually runs. So now let's do some benchmarking. So what I'm going to do here is we can figure out the inference time for a batch or an image and the number of images that we process per second. So we can come here and run the number of cores. So we have 2 different options available. So I'm going to pick the 4 core just to keep it simple here. And then what we can do is we can run a couple of different batch sizes. So we offer anywhere from 1 to 64. So why don't we do this? Why don't we run batch size 8 and batch size 64? So we can run 2 of those. Since it's MobileNet, it'll run pretty quickly. And so the purpose of this, and we share this as part of our beta program, is to allow you to run this on your own environment so you can see how it runs, right? So, in this instance, I'm running on AWS. You might be running on your own machines in your data center. You might be running on a different cloud environment. So you can compare the performance here with what you'd expect from your typical environments. All right, so we can set up our benchmark process. So what's happening here is we're setting up a set of warm-up iterations. We run 10 warm-up iterations, then we do 100 test iterations. We set our input size. We run through warm-up, and then we determine what our outputs are going to be for purposes of benchmarking. And now we can run with all of our combinations. And so it's going to run through the benchmarking process. So what you'll see here is it's doing just what we described. So it's running MobileNet recal at batch size 64 across 4 cores, batch size 8 across 4 cores. Tell me how many iterations it can run per second. Yep, and that's what we run. And then we can do a quick visualization. And so what you'll see here is we display it both as a chart and a table. So what you can see is batch time, the image time per image in each of these, and then the images per second. So as I said, this is a demo that we allow you to run in your own environment as part of our beta program. And so, if you're running the models that we have, you can test the performance of this, end to end versus what you'd expect it to see based on the current setup you have. And you can see straight up how well the solution's performing, all self-contained in with the Jupyter Notebook. And then Once you do that, the next step is to go in and start to run it on your data on one of our models, and then eventually your own model and your own data. So that is the demo today. So let me switch back over to slides, and then I'll get back over to Q&A, and we'll see how we're doing here. All right. So a couple questions here. So this is one is from Jarek. Do we compare in our benchmarking slides the same models pruned on both CPU and GPU? We did, although what the same models that we ran in dense mode, so MobileNet and EfficientNet. We didn't run the prune ResNet, I don't believe, on the GPU because I don't think the GPU can execute the prune version. All right. All right. So Peppo asked, you said you were currently focused on computer vision and image applications, specifically recognition and detection. And is there, so essentially the question is why, and is it related to pruning of those models? And so it really isn't. It's really a matter of focus. So as you guys know, models have, it's not tied to pruning per se, but models have obviously the full model architecture, and then they have their operators within, so convolutions, ReLUs, non-maximal suppressions, all the different things, fully connected layers that make up the model. And so, as a startup, we're trying to remain focused so we can focus on getting performance out of the operators that are consistent across a wide range of these models without having to proceed through the whole long tail of all the operators that are available for all models, right? And so, the analysis that we do is we look at each new category of model type, like segmentation, and we say, hey, what are the operators within those models that we need to add support for to get performance? As an example, things like concats. And then we can plan out how do we add those into our models as we build that repository. We can run lots of all the models and many of the operators within those, but what we're focused on is from a go-to-market perspective is what are the models and where do we get the most performance? How do we optimize those? We're not just running them to ensure that the model doesn't fail. All right, so then let me just move here. So this is the last slide. I'm going to switch over to the rest of the questions we have here. So to summarize the session today, so it's really about what we talked about today is delivering deep learning performance with all the flexibility of software and taking advantage of the abundant CPU resources you already have available, be it in your cloud fleet, in your data center, and your Spark clusters, and turning them into capable resources for deep learning applications. In this time of uncertainty and all the things happening in the world, there's a tremendous opportunity to reduce costs for deep learning deployments by running them on CPUs. What we've talked to lots of VPs of engineering who have, sort of runaway, GPUs out and running in the cloud. It's a way to bring some control into that, put them on a much lower cost resources and reduce the IRR necessary for those applications to be either deployed initially or to be delivering returns back to the business. As you can see, we accelerate lots of real-time results for computer vision apps in that area. And because this is all software, we can fit seamlessly into your existing deployment pipelines. So what can you do for next steps? So first up, we'd love for you to sign up for our early access program. We're in private beta for our 1.0 release. We're working with our first handset of customers, some of whom are here today. So we thank you for those. And if you're interested in joining our private beta and want to work with us with some of the model supports, model architectures we support and classification detection, we'd love to have that conversation. You can sign up right on the website and we'll reach out to you. Second, you can take the deep learning survey. That's still available, and so it's been very insightful. We published a blog post with our initial resources from the first almost 300 responses, but we'd love your insights. And you can send us an email at learnmore@neuralmagic.com if you have additional questions. And always, you can congratulations and celebrate Cinco de Mayo. I'm going to go through and look at some of the Twitter questions. So one question was, how can one start using your software? What environments can we run it on? Local, containers, kernels? So the best way to start is to sign up for the early access, and then you can run it. We talked a bunch of different places you can run it. You can run it on your local machine as long as it is x86. You can run it in a Docker container or what have you. So there's lots of ways we can do that. I'd love to talk specifically about what your requirements are. Another question, is there an open source or free package available? So we don't have a free version available today, but that is certainly something we spent a lot of time talking about. And ultimately, we think in our plans is to have a permanently free tier. And the question right now we're asking ourselves is what would be included in that would deliver value in and of itself to developers, both for an evaluation, but as long-term value to them. And then, as with all good open source projects that are sort of enterprise oriented, is also then have value add components that would, from a business perspective, would enable you to get more capabilities out of the free software, take advantage of more resources, more tooling, or management consoles or what have you, and get more value from it. So very much on our path, and something we're considering. In the beginning right now, we're in our beta program, which is free, and then we envision we'll have a 30-day free trial as a way to foster evaluations as people are considering the software. William asked, do we have any customers using Neural Magic and Kubernetes clusters? So we're just testing in Kubernetes clusters. So maybe if that's interesting, we'd love to talk to you about it. We certainly believe that that's going to be the future for deployments, and want to encourage you to talk to us about that. And we'd love to learn more, and we see that as an opportunity for us. But we're at the early stages of testing that from a deployment side. So lots to learn there for sure. So Javier asked, how does the performance compare between running models on a CPU with or without Neural Magic? Great question. So what we're seeing is, we've compared against Onyx runtime, where on a CPU where you see performance, you can watch the video right on the homepage of our website. It's usually on average 10x or better than the Onyx runtime. We've compared it against a number of the software kits that are available from some of the vendors like Intel, and we're anywhere from 2 to 10x better than those. So we certainly see significant improvement both on dense models and on sparse models compared to other CPU solutions as well. Well, someone asked, is the notebook available externally to play around with? So it is not available externally today outside the private beta program, but we'd love for you to sign up for the beta. Will the slides be sent out later? Yes. So the recording and the slides will be available as part of this session. Another question, is there hyperparameter auto tuning? Do these decisions have to be made manually? Great question. So we do it 2 different ways. One, we can do sort of you can do it sort of model wide and sort of one shot, if you will, across the model, or you can click down and do it on a layer by layer basis. And as I mentioned, we're going to increasingly add automation, so there's less iteration and sort of less, craftsmanship for the data scientists in sort of determining what the optimum sparsification levels are within a model. So there's lots of innovation here. Our 1.0 we're excited about, but we have a great roadmap with regards to the recal tooling. Let's see. So Calogero asked, do you support structured pruning also of transformers like BERT or Turing NLG? So we don't support transformers just yet. It's something we're investigating. And this is really for a matter of focus. We certainly believe that transformers are really valuable and a great opportunity area, and both all of our set of algorithms will apply really well there. So we're optimistic we'll get performance, but we have not started on that. And Jackie asked, where do we stand out? How do we stand out from OpenVINO? So we've done some initial testing against OpenVINO, apples to apples at FP32, where we see ourselves anywhere from 2 to 8x faster. And we're building in quantization. So, our belief is, there's a great toolkit there, but we believe we can get better accuracy and better performance for both sparsification and quantization. So we're really bullish on that one as well. Let's see. All right. So I think that's all the questions that I've seen. I also want to announce that Manny Sarkar from London is going to win the Margarita kit. So congratulations, Manny, for these for being the most active questions, and so hopefully you'll have a good Cinco de Mayo and think of Neural Magic when you do. So appreciate that. And I want to thank everyone for your time today. We're at the top of the hour, so thank you for joining us. We look forward to talking to you in person, and have a great day.